And so what causes this background blur? And so no, it's not this chip, but I'm using this chip just as a representative. This is basically just a sensor. So if we think about a digital sensor, we know something about it. We know that it captures light, and we know that it captures light onto pixels. So usually we have this concept of megapixels, and people are always saying more megapixels is better, etc. But luckily, as hopefully you remember, I said that's not necessarily true. But these pixels on a sensor have a fixed size. They're only so large, and so that means that they're only able to capture a certain amount of detail or a certain amount of light. And so there's going to be another diagram up here that I don't want you to get confused immediately by. Let me explain it for a little bit, and hopefully it will make a little bit more sense. Now, let's say that we have a lens. So we have this lens right here. It's oversimplified, of course, and we have this light that enters the lens from the upper right-hand corner. And so this lens, of course, focuses the light, and it will ideally focus it onto our sensor. And so what we've been talking about before with a lot of the diagrams that I've shown before is that the lens will actually focus the light onto one exact tiny, tiny little point. And that will show up as a dot, basically, as a little, if you imagine, for example, stars. If you take a photo of a star field, each little star is a little dot, and all of this light has to converge onto a dot on the sensor for it to appear that way. Now that's sort of what's going on here. We have this light that's coming from very, very far away. We have to focus it onto this dot. But the pixels on the sensor itself aren't infinitely small. They do have, even though they're very tiny, they do have a certain amount of width, and they do have a certain amount of height. So that means that there is a range of allowed sharpness, basically, that this lens can focus on. So if we have this concept right here, so let's say that we have a circular pixel, and we give it a certain size. Now, any amount of light that's focused that's smaller than that, it will still appear as a dot. It's not going to be any sharper in the end image if it's any more focused than this, for example. So we have this range of allowed sharpness that can exist within an image. And so I've marked here something called the COC, or what's called the circle of confusion. I really wish whoever came up with that didn't call it that, because I think it just helps make it more confusing. But you can think of this circle of confusion as being sort of the smallest little tiny pixel, so to speak, that is allowed for us to make something sharp. So it's not exactly one pixel, but it's actually it's a bit more complex. It involves how we actually view the end result. So if we are very, very zoomed in on an image, for example, when we're looking at it on our computer screen, then as you know, things can look a little bit blurrier than if we are not as zoomed in on that particular image on our computer screen. That's one factor that we have to take into account. But we can generalize this and just say that there's this one little circle, this one little bit of area, and if that lens focuses the light onto that area or smaller, anything that's that area or smaller, it will appear to be sharp. It will appear to be in focus. Because if that light goes over to the next pixel, for example, then it's occupying 2 pixels. It's not going to be exactly sharp. It's not going to be exactly one dot on the image. It will appear to be slightly blurry, for example. And so then we have this range through which something can be acceptably in focus as it becomes focused by the lens and onto the sensor. Now, we're talking about very, very small amounts for the circle of confusion. So for a typical digital SLR nowadays, we're probably talking about a circle of confusion diameter that's about 0.01 or 0.02 millimeters. So very, very, very small. And so any light that focuses on, basically focuses larger than that, it's going to be blurry, and we are going to see this background blur. And so that's where this depth of field comes from. So anything that is larger than that, and so remember that this is meant to show you not exactly where the sensor is going to be necessarily, but just as this lens focuses the light, there is a range through which that light will appear to be in focus. So if our sensor was anywhere within this region right here, then it will appear to be in focus. But if it's outside that region, so maybe back here, for example, or over here, then that dot is not going to be in focus. And that's all that this range is telling us. So to look at it now, in terms of aperture, in terms of the f number, let's say that we have a very, very large aperture and we have light that's coming in from the very outermost extremes of the lens. And as it goes through this aperture, and remember that the aperture isn't necessarily the front element, it's not the very front piece of glass, it could be something inside that's actually limiting the aperture. As it goes through that aperture, you can see that if we have a particular circle of confusion, we have this depth of focus here. Now if we stop down the aperture so that we basically make the light narrower, then it's going to be a lot longer. So when we bend this light, it's going to be a lot longer like this, and we therefore have a wider range through which our subjects can be in focus. So again, for this top aperture, our sensor could be anywhere along here and be in focus. But for our bottom one, it could be anywhere along this range, which means that something over here, if our sensor is over here, then that object will still be in focus. Whereas if we had it with this larger aperture, it would not be in focus anymore. And in fact, if you've ever taken a photo with your digital camera, with your digital SLR, and noticed that at higher f numbers you see dust more, you see it better than you do in lower apertures, it's basically for the same reason, in that larger apertures, the light comes in at a greater angle versus the smaller apertures or the higher f numbers, where light comes in a bit straighter. And so if you have any dust on the sensor somewhere, then the straight light is going to cause a shadow onto the sensor right underneath it, whereas these sharper angles just are not going to cause so much of the shadow. Now, there is something that we do have to watch out for as well, and that is as you make this aperture smaller and smaller and smaller, we actually have this other physical effect that happens to light called diffraction, and it can actually make things a little bit softer. So even though you can make the aperture so small that pretty much everything is in focus, you have this idea of diffraction that can actually that disperses the light in such a way that it becomes blurry and it doesn't look in focus. Okay, but using depth of field, you can, of course, get these effects that you want. So you can alter the amount of background blur that you want by having a lower f number. And so the lower f number, again, causes these stronger angles of light, which means that it's a lower range for us to fit that light within the circle of confusion, and therefore we have less of a depth of field, or we have less of a depth of focus and a longer depth of field. But we can, but one of the things that lenses can do in terms of the background blur is, well, no, let me rephrase that. So other than just affecting the amount of background blur that we have, the lens that you are using can also affect the quality of the background blur as well. And this is something that as you get to purchase more expensive lenses, you will start to notice that the background blur looks a little bit different. Maybe it looks a little bit smoother than in some of these less expensive lenses. And there's a very good reason for this. So if we take a look at this image here, for example, you'll notice that we have some lights, or some basically they're just reflections really, that are slightly out of focus. But if you look very closely at this one, for example, it's actually not perfectly round. It actually has a bit of a geometric shape to it. So if we zoom in, zoom in, zoom in, zoom in, you notice that hopefully it's more obvious now that it is not a perfect circle, and in fact it's more hexagonal. We have 6 sides to this particular out of focus region. And the reason for that is the aperture itself. Now if you remember, when I passed around the camera and you pushed that button and you saw the aperture fold down, it was basically like these metal leaves that collapsed down and made a smaller hole. And sometimes some lenses don't have don't cause an aperture that's perfectly circular. They will actually have like 6 leaves, for example, that collapse down and actually make a hexagon. And because all of the light comes through that aperture, and even if it's out of focus, like say here, for example, you will actually see the geometric shape that's created by the aperture in out of focus areas. And so you can get some really, really strange out of focus effects, or what we call bokeh, which is basically the quality of the out of focus blur, by using lenses that have different properties. So a typical camera lens, you would see something like this. And actually, now that I've pointed this out to you, if you go home and you watch TV tonight, you will probably start to notice some of these things a little bit more. And it's going to bother you to no end when these TV shows start using lenses where their out of focus blur causes these very polygonal areas like hexagons or pentagons or worse, squares or triangles. I don't know. I don't think you'll see anything like that. But it's really going to bother you, and you will start to notice when they're using higher quality lenses that can actually have circles that are, in the background blur. Now, you can actually get some really funky stuff if you use lenses that are not typical camera lenses. So just as an example, I connected my camera a long time ago to a friend's telescope. And we calculated that the end focal length was about 2,000 millimeters. So it's very long focal length. And just to give you an idea, this was when I was living in the dorms at MIT, which was on the Cambridge side of the river. And we took it outside and set it up, and then we pointed it towards the Prue, and we wanted to see just how much we would be able to view. And that's this image here. And in the full image, it's actually uncropped. It's just resized. In the full image, you can actually read the exit signs within it. And the Prue is a quarter mile away, or is it a quarter mile? No, it must be a mile and a quarter away, something like that. It's really far away, and you can see a lot of stuff. But because this was a Schmidt-Cassegrain telescope, that means that it's a reflector, which means that the light comes in, there's a mirror in the back, then there's a smaller mirror in front where the light comes up where you can view it. There is a mirror right in the middle of the image. And so in the out of focus images, you actually get this donut effect. You get this weird out of focus shape that is really distracting and is not something that I think I would consider acceptable in a typical image if I was just using it in my day-to-day images. And in fact, if you are purchasing a camera or if you are purchasing a lens and you see a very long lens like 500 millimeters or 600 millimeters or something like that, and it's dirt cheap and it looks super small, it's most likely a mirror lens, a lens that's going to give you something like this because it folds the light by having a mirror in the front and in the back of the lens to basically reflect the light and make the focal length longer. And that really reduces the cost of these lenses, but it also gives you weird effects like this. And also the aperture is really, really small because these lenses are small, so you lose the ability to autofocus, and it's just a nightmare. So don't even bother wasting your money on these novelty mirror lenses because it's not really going to be much fun, except for something kind of sketchy like this, where you're trying to take the photo of a very, very far away building. Now, the number okay, so to go off this tangent, the number of blades that exist to form the aperture actually make a big difference to the bokeh. But there is a lot of other stuff that goes into bokeh as well. So, and there's quite a few people that are very, very stringent about how their out of focus dots essentially look. And they look at not only how circular it is, but also how uniform it is, if there's any sort of ripplings of color. So if there's any hint of, let's say, a donut shape, so nothing like this, but even just, maybe there's like a little bit of a halo or something like that, all of this stuff falls into this very broad term of bokeh. And it's not the quantity of background blur. That's not what we're referring to. We're referring to the quality of the background blur. And there was this, let's see, I hope this website still works, but there was this one guy who basically did a bokeh test on a number of, lenses, and he explains it actually pretty well. And I'll put this online, but he goes through quite a bit of stuff, but he also does a very good job of showing you what is good and what is bad bokeh. So for example, here we have relatively good bokeh because it's circular and it's uniform, whereas here we have that halo problem that I was talking about. And this can contribute to having a background blur that's, rather than being smooth and contributes to the look of the image, it could be sort of harsh in some way, and just in this sort of indescribable way, harsh and distracting to the final image. And so whether you like it or not, this stuff does affect the end result of the image, but it doesn't mean that you should dump all of your inexpensive lenses and go for the most expensive things out there. This is just something that you should be aware of, and something that people do notice. In fact, one of the things that bothers me recently is that I was at a hotel in New York, a Marriott actually, and they seem to be catching this sort of postmodern art thing where they have some photos up that that's used to decorate the place, but the photos are strictly out of focus. It's just like some street lights that somebody doesn't know, he doesn't know how to operate his camera, and so he takes a picture and it's completely out of focus, and it's basically like red light and a green light and like a blue light that's completely out of focus. And it bothers me that the bokeh was terrible. Like, that's the whole point of the image, was this background blur, but it was like spotty, and it just looked horrible. It was hexagonal, and no way. All right, anyways. So hopefully now that will bother you as much as it bothers me, so I don't have to be alone in this. Now, going the other end, if you want to eliminate background blur entirely, we actually have this concept called the hyperfocal distance. So whereas before you knew that the best way to eliminate background blur was just to have an F number that was the largest you could possibly do without reaching into the problems of diffraction, you can actually use something called the hyperfocal distance to try to get even more in focus. And basically, you don't need a fancy camera to do this. You just need a camera that can where you can set the aperture and you are able to focus on something of your design, or something that you want to focus on. Excuse me. And what this allows you to do is to take a photo of everything from, let's say, one half, or it's not, let's say, it is exactly one half the distance of whatever it is you focused on, all the way to infinity. So there is some exact point for your exact camera and lens and F number configuration where you can dictate this point that is exactly so many feet away. So in this camera, let's just say it's right here. If you focus on me at this point, everything from half the distance from me to the camera all the way to infinity will be in focus. And there's a couple of ways that we can figure out what that distance is for your particular camera. I'm showing you the scary way first, and then I'll show you the easier way. But there is, of course, an equation for this. So if we want to figure out the hyperfocal distance, h, we just take the focal length, square it, divide it by the F number, and divide it by the minimum circle of confusion diameter. Remember that circle of confusion? I hope you're not confused yet, because it's reared its ugly head yet again. So if you know these values, the focal length, which you should be able to determine based on, usually there's a little zoom range on the camera when you're zooming in or out, or you can even look on the front of the camera if you have a compact digital camera, for example, and you just know, let's say, the widest focal length and the longest focal length, then you will be able to set it to one of those, for example, and know that focal length. Then you can figure out the F number, which you should know because you'll be setting it, and the minimum circle of confusion diameter you can look up online. There's a couple of nice tools that allow you to do this. And in fact, the easy way to do this, frankly, is not to use that equation, but instead to go to this website called dofmaster.com. And here they have nice calculators and tutorials and even iPhone apps and printable graphs, all sorts of stuff. You can just pick your poison, figure out which one works best for you, set all of these things yourself in their fancy little app or in their complex little graph, and be able to figure out exactly what the hyperfocal distance is. Now, remember that when you calculate the hyperfocal distance, it's going to be some number like, let's say in feet, for example. And so you will try to focus on something that's that many feet away, and when you do that, you will achieve this hyperfocal distance. You will get everything from half the distance all the way to infinity in focus. You just get that sort of for free by using this calculation and for focusing on something at that particular distance. Now, if you happen to have an old school camera with an old school lens, I guess, rather than an old school camera, and you have this sort of aperture and focal length window on your lens, then this will help you out a lot, because you can actually figure out what the hyperfocal distance is just by looking at it, basically. And so in this old example, we have a lens where you are focusing in on something, and then it tells you via this graph up top how far away that object is. And so it tells it to you in not only feet, but also in meters. Now, when you set the F number, you'll notice that it's color-coded. So, for example, F16 is green, and so if you, or rather cyan, this sort of light blue. And so if you set it to F16, then what you can do is look at this graph, and you will see everywhere from this light blue line all the way to this light blue line will be in focus on that camera. So you can set it to whatever's in focus, it will be in that range that is in focus. Now, if you set the very leftmost part of this range at the infinity point, you are automatically setting the hyperfocal distance, because you will notice that you are getting everything from half of your focal distance, or half of your focus distance of about, I don't know, like 5.5 or so, almost, 5.25, I guess, all the way to about, 2.75 or something like that. You're getting from half of that distance all the way to infinity, and so you're able to maximize the focal range, or rather the amount of objects that are in focus in your particular image. Now, this is definitely the easiest way to go about calculating it, but unfortunately we don't have windows like this anymore, because we just don't have the need to know this sort of data in a very analog way. And in fact, if you have a camera, or if you have a lens that's expensive enough to even have a focus distance window, it will typically be oversimplified like this, where you just have one line that indicates the focus distance, and that's it. You don't get any of the other information. So unfortunately, we have to use these more complicated ways of calculating and using the hyperfocal distance. So again, go to dofmaster.com, and you'll be able to solve this pretty easily. Or if you use this very fancy equation, you will be able to accomplish the same thing.